First of all, I have to apologise. My voice might break. Um, I went to a pop concert on Saturday night with Ed Sheeran, and I was singing, and then I realised actually I have to stop because I have a talk to give. So as you can see the title, and I'm the Japanese representative here at the conference. So we're working with Rydberg atoms and waveguides, and I can give you a lot of motivation as to why we're working with Rydberg atoms and waveguides. The main reason is because we thought it would be cool and everyone told us you can't do it. So that's always a strong motivation to try to do something experimentally. Anyway, there are several types of waveguides that people work with in general for ground state atoms. So in the Kimball and Chen group, they work with alligator photonic crystal waveguides. There are hollow core fiber. Many people have tried working with hollow core fibers and putting atoms inside them. Many groups continue to try working with hollow core fibers. I have a student from a group in Italy spending quite a bit of his PhD with me at the moment, and his main PhD project back in Italy is working with hollow core fibers. There are also photonic crystal waveguides, which are a bit different to these alligator photonic crystal waveguides. And again, Vuletic, Lucan have been probably some of the strongest people working with these photonic crystal waveguides. And then you get to more exotic types of waveguides, such as these coplanar waveguides. And then you come to the optical nanofiber, which honestly is so simple compared to these fancy structures. So with regard to simplicity, it's almost comparable to the hollow core fiber. However, it's even simpler. Julien works with them, and the concept behind them is very simple, but actually working with them in atomic systems, maybe not so. So the hollow core fiber is just a tapered silica fiber, and you can see that there are many groups working with hollow core with tapered fibers. And I said one of the more reasons for that is because the simplicity actually fabricating it. You don't need nanofab facilities. You don't need fancy fiber. You just work with commercial silica fiber for whatever your wavelengths are. So these optical nanofibers, if I compare them in size to red blood cells, so this here is just the cross section of a standard typical fiber, 125 microns with maybe a diameter of 5 to 10 micron. Red blood cells, typically about 5 micron. Human hair, depending on the color of your hair, is somewhere around 50 micron. And this from the Bath group, who were one of the first groups working with these fibers just for photonics purposes, is a 2 micron fiber. And one of the main advantages of these fibers, aside from their simplicity in making them, is that similar to some of the effects that Sonia was talking about earlier on, you have this longitudinal polarization component. So you can play with that when you're working with atomic physics, but also there is the fact that if you're trying to do a very tightly focused beam to have some of these effects, you end up with a limit due to the Rayleigh range. So your tight focus, you're focusing down to 1 micron, you can try to define some figure of merit where the distance over which you're reasonably focused divided by the focal spot is somewhere around 10, and that's being very generous. Whereas for the very thin fibers, what we end up with is more or less no condition on the length of our fiber, and the equivalent behavior ends up being all along this length. So we can end up with more than a factor of 10,000. So, typically in cold atoms, we're working with fibers which are a few millimeters long in this nanofiber region. So this here is the nanofiber region. This is just normal commercial fiber. You can go to tens of centimeters, even I think very close to 1 meter. But of course, no atoms experiment can fit a 1 meter fiber into it. They're quite easy to make. So my first attempt at making them was literally in the lab, me and the student pulling them with our hands and using a creme brulee burner to make them. You're not going to use that in your atom system, but it does allow you to make tapered fiber. You also get very nice effects in the fiber itself. So you end up with putting very small powers into the fiber. You have an extremely high field intensity here. So our weights typically, so the diameter of our fiber is around 300 to 350 nanometers. And then, as I mentioned, these are just fibers at the end. So you just connect it to your laser, connect it to your detector, connect it to whatever fiber components you want. So integration into an experiment is very easy. This is just an SE image of one of our fibers. This is a 385 nanometer diameter fiber. And here you have the very, very smooth taper region going down to that very thin diameter. Okay, so I mentioned that the motivation behind this was because we were told we couldn't do it, but that's not the only motivation. So I was chatting with some groups in France, in Paris, when I was on leave there, and we were talking about these papers by Etienne Briand and Klaus Müllmer, where they were talking about developing quantum repeaters using Rydberg atoms. And of course, this is a theoretical paper. So they were going to have Rydberg atoms within cavities. These cavities were going to be linked by fiber systems. And you'd have multiple of these in order to create quantum nodes. So while I was chatting with them, we thought, okay, let's try and simplify this problem. Let's take away these macroscopic cavities and let's just try to have the Rydberg atoms along the fiber. If we can do that, we could later, maybe in 20 years, maybe 5 years, try to put on the cavities on these fibers. So you can put cavities on these nanofibers. That's not a problem. So you can have everything integrated into your fiber system. So that was the primary motivation behind trying this. The other motivation, of course, was what I said, that people said, you can't do it. And maybe you can't because we're still the only people with the results. So we'd like others to try. So this is the experimental setup. Have one of these tapered fibers, quite a short waist, a few millimeters. Then the red blobs here are indicating Rydberg atoms, and the yellow are indicating just normal, normal Mott ground state atoms. And a couple of first questions: can you even do this? My atoms are going to be so close to my fiber. I'm going to be a couple of 100 nanometers away from my fiber, my dielectric surface. The Rydberg atom is highly excited atom. That electron is going to be stripped by the dielectric. So that was the first question. Second question, what happens to Rydberg blockade? Well, we don't know, okay? So we did a series of papers, of theory papers then with, led by Etienne Briand, but also with Klaus Müllmer, about looking at atoms next to fibers. Of course, theoreticians work with one atom next to fiber, starting with sodium atom because it was easier, and it didn't look very promising. So then we said, okay, well, that's not really realistic. It's a single atom. And then they did more papers. And then looking at atomic ensembles, which is what we have, it seems to be quite promising that maybe there will be some coupling into the modes of the fiber that can be useful. So then what about Rydberg atoms, just in case you're a photon person and aren't too familiar with them. So what we're dealing with are highly excited neutral atoms. They've got a very long range interactions, which is really nice. And they have this blockade effect, which I said is one of the primary reasons why they're used in quantum information, but I won't go into it too much here. Effectively, it means that when you're looking at your energy levels, they get shifted due to a van der Waals interaction. So in a certain sphere, you can create one Rydberg atom, but you won't be able to create two Rydberg atoms. So then the experiment, we have essentially, we believe, demonstrates that you can do Rydberg atoms next to dielectric medium. We have shown what the limitation seems to be, at least for rubidium atoms. We've looked at s and d orbitals. We can't access the p orbitals at the moment. And it's a 2-photon process. So this is our cold atom laser, and then we propagate this 480 Rydberg excitation through the fiber, and we essentially look at the atom loss in the atomic system when we turn on the Rydberg laser. So this is just the timing of the experiment for the experimentalists. Obviously, that's just a very simple timing. It's much more complicated than that. But these are the two things we care about. We load our atom trap, we turn on our Rydberg laser, we lose loads of atoms, and then we look at this value here, N2, as a function of the frequency of our laser. No, we do not believe this huge loss of atoms from the magneto-optical trap. We do not believe they are all Rydberg atoms. However, people often miss the time scale here. This is a loss over a couple of seconds. So here we have time for atoms to move in and out of our interaction region. And we then change the frequency of our 480 nanometer laser for different energy levels, this 29D 5/2 and 29D 3/2. And we start seeing these sort of features, which is what we expect. You can view this as an Outler-Town splitting of the intermediate, or you can view it as a coherent and incoherent process within the system. We go to the S level, we see much more pronounced behavior, which actually is different to what the Rydberg community expected us to see. So these are the sort of signals that we look at. So we see a frequency dependence in the generation of the Rydberg. We can't look at the Rydberg directly. We then said, okay, how high can we go? So we tuned our laser to the S transitions. We went to n equals 55. The D transition, D3/2, n equals 65, and n equals 68. So then we just can't create the Rydberg anymore. We can't create the Rydberg literally anymore. We have to move to a different part of our nanofiber. So we have done something to our nanofiber with regards to charges. We can go back a couple of days later, or maybe a couple of weeks later, and use the original part of nanofiber again. So it's something transient that doesn't last. What's actually happening here if we think of the size of our Rydberg? So we've got a very large Rydberg when we go to n equals 67, very small when we go to n equals 29, comparatively speaking. And if we think of this in terms of the evanescent field from the fiber, this one is essentially going to be very close to the fiber when it's either being generated, or it has to be generated very far away here where the interaction is much less. So this is more or less what we're studying at the moment, this behavior relative to the atom position. So then, to try to get some control of this position, we need to introduce dipole traps. Okay, this is a hot topic talk. I cannot go into dipole traps. It's just a way of getting a uniform array of ground state atoms next to the fiber. If we manage to generate the ground state, we then release them and do the Rydberg excitation. So this is what we're working on at the moment. This just shows you the potential you can get in these dipole traps around the fibers. However, when we do this experiment, we see new features appearing. So we're turning on our dipole trap beams, and we start seeing these features. That's okay, up to 35d5/2. But then when we go to even higher energy levels, it's a mess, okay? So here, Central European Workshop Quantum Optics, loads of great theoreticians who love multi-level atoms. We would love your help. So currently we're working with Rob Löw in Stuttgart, but he's also an experimentalist, trying to understand what on earth is going on here when we turn on our trapping beams. We know it's due to light intensity. We know it's due to ionization of our atoms. We know it's due to charging of our fiber, but what the overall combination is, we don't know. It again is transient. We go back half an hour later, this effect is gone. Okay, so it just appears over about 15 minutes timing. So this is where we are. We're looking at those shifts. We're working on publishing some work. So I'm giving you some unpublished work because we're still trying to figure it all out. And what we're also looking at is alternative trapping strategies where we won't have these high fields, where we can reduce the fields a little. So one of these on the archive, the other one isn't. Okay, so thank you.
So thank you very much. Any questions?
And for those looking, yes, this is how a research group in physics should look, okay? Very, very diverse. My atom group is essentially all female at this stage. Yeah, Julien.
Yes, thank you, Julien. I have a question about the trapping. So you said it's hard to trap your Rydberg. What people did in free space was some bottle trap.
Sorry?
In free space,
yeah,
many groups was trying to make a bottle trap, which is dark in the center.
Yeah.
With all your work before with higher spatial modes, maybe there is a way to go into this direction with the nanofiber.
So there's just a paper on the archive now with Etienne. We're talking about 5 traps around the fiber. It's a theoretical paper, but you'll see in the conclusion, we do have a comment where maybe higher order modes could be used. Okay, so we think that there probably are some advantages of higher modes in this. Yeah, thanks.
Thank you very much. Let us thank the speaker.